Okay, and this last problem, number 5, we'll be doing the same as a couple other problems in this practice exam, but the only difference is we actually have an external force being applied. All right. Since we have an external force being applied, that means that it's not going to be equal to 0, and we can't necessarily solve by getting y sub h. So I'm going to go ahead and solve for all the different variables. So in this case, mass equals 1 kilogram. And that mass is hanging from a spring from a ceiling, and it comes to rest at equilibrium. So that implies y of 0, y prime of 0 equals 0. The reason that is that it's at rest, at equilibrium. So y of 0 and y prime of 0 both equal 0. And an external force of 32 cosine 4t is applied. So this is our f of t, which is 32 cosine 4t. And the spring constant K equals 16 newtons per meter. And then the damping constant, B, is 4 newton seconds per meter. So then we have to write the described dE above with the initial conditions. So it's going to be y double prime plus 4y prime plus 8y. Instead of equal to 0, it's equal to f of t, which is 32 cosine 4t. Initial conditions, like I said, y of 0 equals y prime of 0, which equals 0. So I need to determine the steady state solution. So in this case, steady state solution, like we said from the other problem we did, the series circuit, SS implies y sub p. So before we can determine our y sub p, we need to solve for our y sub h. So our y sub h is dependent upon the auxiliary equation, so which is r squared plus 4r plus 8r, sorry, just 8, equals 0, which implies r1, comma, r2 equals negative b and negative 4 plus or minus the square root of b squared, which is 16 minus 4ac, so 4 times 8, 32, all over 2a, 2 times 1, and this equals negative 2 plus or minus, becomes 4i, 2i. So the reason why we do this is so that we solve for our y sub p, we don't have any repeating roots. So we solve for y sub p, it equals a cosine 4t, because remember it's dependent upon the right side of the equation, which is 32 cosine 4t, plus b sine 4t. Now if you look, our beta for this is 4, the beta here is equal to 2, so no repeating roots. So although it didn't seem to matter, it's important that you do check for y sub h whenever you solve for steady state. So now for y sub p, we need to solve for y sub p prime and y sub p double prime to put back into the equation, which equals 4a sine t, which would be negative 4t, plus 4b cosine 4t, y double prime equals negative 16a cosine 4t plus 16 minus 16 b sine 4t. So now what I'm going to end up doing is plugging this back into the original equation. I'm going to try to make some room because I did not give myself enough room for this problem. Nor will the Christian Parsons. It's hard to fit. It's just they have so many problems and it's hard to fit all of it onto one exam. So you might be pressed for space. So try to write small and neat, so you don't lose track of anything. So now I'm going to plug this in. So we have y double prime, which is negative 16 a cosine 4t minus 16b sine 4t plus 4 times negative a sine 4t plus 4b cosine 4t plus 8 times y sub p, which is a cosine 4t plus b sine 4t, and this is all equal to 32 cosine 4t. I'm going to make this a little bit smaller, fit all on the page. Going to switch to a different color so it's easier to track what I'm doing. So now we have, so this right here is 16a cosine 4t, 16b, negative 16b sine 4t. Let's see if there's any major things we can cross out. Oh, just realized I made a mistake because I could have sworn this crossed out. So this is actually supposed to be 16. I miswrote that. So this right here is supposed to be 16. This right here is supposed to be 64, which is going to make this 2 square root 3i. Either way, there's no repeating roots because our beta equals 2 root 3, but that's my bad. And I don't feel like redoing this entire problem just to make that little error, so I'm going to make that note now. So underline that, so that's my bad. So now we have negative 16a cosine 4t, negative 16b sine 4t. We have the positive 16a cosine 4t and 16b sine 4t. So that means that these terms right here cancel each other out. And we're left with negative 16a sine 4t plus 16b cosine 4t equals 32 cosine 4t. And then we can equate like coefficients. We have a sine equation, and that will be negative 16a, which equals 0, plus a equals 0, and then a cosine equation, which is 16b equal to 32, which implies b equals 2, which implies our YSS, steady state, which is y sub p, is just 2 sine 4t. So now, is the system at resonance? Justify. So we need to solve for our resonant frequency. So that's going to be gamma r. So gamma r, and I believe you need to memorize this, so make sure you remember this equation. I should put it there for a second. I should put star. Remember this. Equals the square root of k over m minus b squared over 2m squared, which equals the square root of 16 over 1 minus b, which is 4 squared over 2, 1 squared. I'm going to double check that. Yeah, b is 4, k is 16, and m is 1. So then this equals the square root of 16 minus 16 over 2, 8. So equals the square root of 8, which equals 2 radical 2, 2 root 2. And so that means that gamma for resonance must equal 2 root 2 in the case of our equation for f of t equals 32 cosine 4t. where 4 equals r omega, or which equals r gamma. This does not equal 2 root 2. Therefore, system not at resonance. And now it asks, if there is no damping, meaning B equals 0, would the system be at resonance? So if B equals 0, so that means our left term, and whenever we do gamma r, goes to 0. So you have k over m minus 0, because B is 0, which would then equal square root of 16 over m, which is 1, 16 over 1, which equals 4. And if we were to look at our, up here at the top, where we had 4 equals omega, which is equal to gamma, and that equals 4, therefore, gamma r, not gamma r, therefore, a system would be at resonance. As I describe the system, let's describe the motion of the system from d versus time. Since the system is at resonance with no damping, the no damping part is really important. The amplitude of the motion will grow boundlessly. As time goes to infinity. And the reasoning for this is because since there's no damping factor, there's nothing that's limiting the spring and from going to its max, its amplitude. And since it's at resonance means that it'll build up and be constructive over time with its waves. So its amplitude will constantly increase with each period that passes. So that's why it will grow boundlessly as t goes to infinity. So it means eventually it will break. The system, whatever the system is, will break because the amplitude is so large. That's why like glass breaks whenever someone hits the right pitch, because it's hitting the resonant frequency, and as time increases at that resonant frequency, the glass, the motion of the molecules in the glass will just cause it to shatter because its amplitude is so high. So for like strings, it doesn't matter as much, but for anything that's rigid, it will cause the system to fail. So understanding how that motion works is very important. And if the system were to be different, say the system did have a damping factor and it was overdamped, then that means that amplitude would eventually go to 0. If it was critically damped, I believe it will go to a constant, and if it's underdamped, and then it will just slowly decrease, and it will go to a number. But understanding resonance and how that affects motion is very important. So, if you have any questions over any of the videos, please let me know in the comments or shoot me an email with a caption or a screenshot or something, and I'll try to answer the questions as quick as I can, as best I can. So, good luck on your test.